So if you want, we can go into the ammeter now.
Yeah.
And then, so on an ammeter, the problem with an ammeter, and if you look at the basic circuit for an ammeter, is you're going to have a meter like this, exactly the same thing. But the problem is an amp, if you want to measure amps, you have to measure it in series. So you have to put this in the circuit. But if your load is 100 amps, you're going to blow your meter, right? So you don't want to do that. So in order to do that, what we do is we install what's called a shunt in parallel with it. And so this little shunt, I have 4 of them here, the big ones, small ones. And if you look at old GE equipment or something like that, you might see these in there because they have a panel ammeter on the front, and then they have one of these. And so 500 amps would run through this. But if you put your little secondary connections, here they are here on right here, you run this to your meter, it only pulls off 1 to 100 milliamps, and that's what runs the meter. And then your 500 amps goes through here. So this is just this is a known built resistance, and we basically shunted the majority of the current through, but a small part goes in a parallel path. Gotcha. And we run the meter the exact same way. So you just redo the scale, calibrate it as needed.
Makes sense to me. Now, can you kind of touch on some of the construction of the shunts? I noticed they have some are air gapped in between the runs, some are solid all the way through. And kind of, can you talk to that to some extent?
Yeah. So I'm going to start off with the, let me find the smallest one here, because let's start the small. So I'm a really big nerd, and I went on each of mine. And so this is the smallest one. This is a 10 amp shunt. And all of them, you might say that they're air gapped. They kind of appear that way, but they're not. They're solid all the way through. It's a solid conductor all the way through. It's just, the thing is we built this in such a way that we know what the resistance is from this point to this point. And they're designed and they're specified in such a way that this would say 10 amps, 75 millivolts. So if I run 10 amps through this from here to here, it will be 75 millivolts of a voltage drop from here to here. And so now you can design your meters that way. And then
now, is there a difference in the various materials used to kind of achieve those resistance levels?
Yeah, so it just depends on what they want to use. Engineers have resistances based off of cross-sectional area, charts based off of material. So copper versus aluminum versus silver. And these are all painted, so that way corrosion never becomes a factor on the shunt. But like this one is just a solid bar all the way through. It's not squirrely like this one right here, but this is a 50 amp shunt. And then this big boy right here, it's all solid bars. It's actually 5 of these solid bars. So that way you know for sure exactly what the known resistance is. And then before they finally secure these and solder them together, there's actually channels in here, and they can just slide this open or closed, and then they could build, I don't know if you can see it really, there's a notch right here, and they can actually, I don't know if I can get there.
I see it. There you go.
Yeah, on each one of those there's a notch, and you can actually just get out there. So if this is off by just a hair, you can get out there with a hacksaw, no joke, and you can just make it a little bit deeper, right? And so that way, if you make it a little bit deeper, you increase the resistance of this, and therefore your voltage drop goes up, and now you just made the shunt exactly to specification.
Now I'm going to have to ask a goofy question. Why does the hacksaw work in increasing the resistance?
So the way it's working is you're actually changing the cross-sectional area, right? So you're taking away conductor material. And so because you take away the conductor, it's like comparing a 14 gauge wire to a 22 gauge wire. So the resistance goes up. That's what happens.
Gotcha.